Metal siding can be bonded to a dwelling. There are several types of fittings used for this purpose. Firstly, self-drilling screws are a common method. These screws penetrate the siding and the beam or sheathing beneath. A washer or neoprene seal is often used to waterproof the connection. Secondly, pop rivets are similar to self-drilling screws. However, they create a permanent blind joint. A backup washer may be required for added strength. Thirdly, locking panels are panels with overlapping seams that interlock. These panels do not require screws or rivets, providing a weathertight seal. Fourthly, standing seam panels are panels with vertical seams that are folded over. These panels have no penetrations through the panels, enhancing weather resistance. Fifthly, hidden fastener systems utilize clips or channels that attach the siding to the underlying structure without visible fasteners. This provides a clean, seamless appearance. Other fittings include flashing, which is used to seal joints, corners, and penetrations, drip edge, which is installed at the bottom of the siding to prevent water seepage, and trim, which is used to cover exposed edges and enhance the aesthetics. The type of fittings used may vary depending on the specific type of metal siding and the underlying structure. It's essential to follow the manufacturer's instructions and guidelines when bonding metal siding. Proper installation is crucial to ensure weather resistance and durability. When working with electrical systems or grounding and bonding, it is essential to adhere to the National Electrical Code, or NEC. The NEC provides comprehensive guidelines and standards for safe electrical installations. Grounding and bonding are critical for protecting people and property from electrical hazards. Grounding creates a low impedance path for fault currents to flow back to the source, allowing overcurrent protective devices like circuit breakers or fuses to trip and to energize the circuit. Bonding connects metallic parts of an electrical system to create an electrically conductive path, ensuring that all bonded parts are at the same electrical potential. This minimizes the risk of electric shock. Article 250.4 in the NEC covers general requirements for grounding and bonding. It emphasizes the importance of creating a permanent and effective ground fault current path. The ground fault current path must be capable of safely carrying the maximum ground fault current likely to be imposed on it. The path should have sufficiently low impedance to facilitate the operation of overcurrent devices. Article 250.8 specifies methods of grounding and bonding. Acceptable methods include using listed grounding and bonding equipment, such as grounding bushings, clamps, and connectors. The equipment must be suitable for the application and installed according to the manufacturer's instructions. Grounding electrodes are covered in Article 250.50 through 250.60. A grounding electrode system typically consists of one or more grounding electrodes connected together. Common types of grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The grounding electrode system must be effectively connected to the earth to provide a stable reference point for the electrical system. Bonding of metal enclosures and equipment is addressed in Article 250.90 to 250.102. Metal enclosures containing electrical conductors or equipment must be bonded together into the grounding electrode system. This includes enclosures for service equipment, switchboards, panel boards, and motor control centers. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of shock. Equipment grounding conductors, or EGs, are used to connect non-current carrying metal parts of equipment to the grounding system. EGC provide a low impedance path for fault currents to flow back to the source. EGC can be wires, cables, or metal raceways. The size of the EGC must be adequate to safely carry the available fault current. Article 250.122 provides guidance on sizing equipment grounding conductors. The size of the EGC is based on the rating of the overcurrent protective device in the circuit. For example, if the overcurrent device is rated at 20 amps, the minimum size of the EGC is 12 American wire gauge copper. For a 60 amp overcurrent device, the minimum size of the EGC is 10 American wire gauge copper. For a 100 amp overcurrent device, the minimum size of the EGC is 8 American wire gauge copper. For a 200 amp overcurrent device, the minimum size of the EGC is 6 American wire gauge copper. Bonding jumpers are used to connect different parts of the grounding and bonding system together. Bonding jumpers ensure that all parts are at the same electrical potential. Bonding jumpers must be sized according to requirements in Article 250.102. The size of the bonding jumper is based on the size of the ungrounded conductors in the circuit. For example, if the ungrounded conductors are 1/0 American wire gauge copper or 3/0 American wire gauge aluminum, the minimum size of the bonding jumper is 8 American wire gauge copper. For ungrounded conductors that are 3/0 American wire gauge copper or 250 kcmil aluminum, the minimum size of the bonding jumper is 6 American wire gauge copper. For ungrounded conductors that are 500 kcmil copper or 800 kcmil aluminum, the minimum size of the bonding jumper is 2 American wire gauge copper. Surge protection is an important aspect of electrical safety. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD divert surge current away from sensitive equipment, preventing damage. Article 280 covers surge protection requirements. SPD must be installed in accordance with the manufacturer's instructions and the NEC. The location and type of SPD should be selected based on the specific application and the level of surge protection required. SPD are typically installed at the service entrance and at downstream panel walls to provide comprehensive surge protection. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electric shock. GFCIs monitor the current flowing in a circuit and detect any imbalances that could indicate a ground fault. If a ground fault is detected, the GFCI quickly trips the circuit, interrupting the flow of electricity and preventing injury. Article 210.8 specifies where GFCI protection is required. GFCI protection is required in bathrooms, kitchens, garages, outdoor locations, and other areas where there is a high risk of electric shock. SI protection is another type of protection, and these are arc fault circuit interrupters. SIs protect against arc faults, which are dangerous electrical conditions that can cause fires. SIs detect arc faults and quickly trip the circuit, preventing a fire from starting. Article 210.12 specifies where SI protection is required. SI protection is typically required in branch circuits that supply bedrooms, living rooms, and other areas where people are likely to be present. Electrical safety is a critical concern in all types of buildings, including residential, commercial, and industrial. Following the NEC guidelines and implementing appropriate grounding, bonding, surge protection, and GFCI/SI protection can significantly reduce the risk of electrical hazards and ensure the safety of people and property. The NEC is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. It is essential for electrical professionals to stay up to date with the latest edition of the NEC and to follow its requirements when designing, installing, and maintaining electrical systems. In addition to the NEC, other standards and regulations may apply to electrical installations depending on the location and type of building. These standards may include local building codes, state electrical codes, and industry-specific standards. It is important to be familiar with all applicable standards and regulations and to comply with them to ensure the safety and legality of electrical installations. Proper training and certification are essential for electrical professionals. Electricians should receive comprehensive training in electrical theory, safety practices, and the NEC. Certification demonstrates that an electrician has the knowledge and skills necessary to perform electrical work safely and competently. Continuing education is also important for electrical professionals to stay up to date with the latest technologies and best practices. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Electrical systems should be inspected periodically by qualified professionals to identify any potential hazards or problems. Maintenance should be performed regularly to keep the system in good working order and to prevent failures. Some common maintenance tasks include tightening connections, cleaning equipment, and replacing worn or damaged components. When working with electrical systems, it is important to use appropriate personal protective equipment, or PPE. PPE includes items such as safety glasses, gloves, and insulated tools. PPE helps to protect workers from electrical shock, burns, and other injuries. It is important to select PPE that is appropriate for the specific task being performed and to use it correctly. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. Lockout/tagout involves disconnecting the equipment from its power source and attaching a lock and tag to the disconnect switch. The lock and tag indicate that the equipment is not to be energized until the work is completed, and the lock and tag are removed by the authorized person. Electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents and injuries. By following safe practices, using appropriate equipment, and staying informed about electrical hazards, we can create a safer environment for ourselves and others. Remember to always turn off the power before working on any electrical equipment. Never overload circuits or extension cords. Keep electrical equipment away from water. Replace frayed or damaged cords immediately. Use ground fault circuit interrupters, or GFCIs, in wet locations. Install arc fault circuit interrupters, or RFCIs, to protect against electrical fires. Test smoke detectors regularly. Have electrical systems inspected periodically by a qualified electrician. If you are not qualified to perform electrical work, hire a licensed electrician to do the job. Do not attempt to repair electrical equipment yourself unless you are properly trained and equipped. Always follow the manufacturer's instructions when installing or using electrical equipment. Be aware of the potential hazards of electricity and take steps to protect yourself and others. By following these simple tips, you can help to prevent electrical accidents and injuries. Electrical safety is not just a matter of following rules and regulations. It is a matter of attitude. We must all be committed to working safely and to protecting ourselves and others from electrical hazards. By making safety a priority, we can create a culture of safety that will help to prevent accidents and injuries. The goal is to ensure that electrical systems are designed, installed, and maintained in a way that protects people and property from harm. This requires a commitment to safety from everyone involved, from the designers and installers to the users and maintainers of the system. By working together, we can create a safer world for all.